Welcome to Dataless U. I'm Paul, coming to you from Brooklyn. Today we're going to take a look at triangle trigonometry. We're going to look at a tough question that involves surveying. In other words, finding the area of a plot of land. We're going to be working out of good old trusty Richard G. Brown's Advanced Mathematics, his Precalculus textbook. If you want to follow along, we'll be doing question number 17 on page 363. So the idea today is to look at a tough question that essentially applies everything that you've learned here in Chapter 9 on triangle trigonometry. Often I find that students will master the individual concepts, but then when challenged to put it all together, say on the final question of the exam, well then there the trouble arises. So let's first take a look at the laws, the main laws or rules or concepts learned here in Chapter 9. I've got them up here on the big board. The first is the law of sines, which says the sine of an angle over its opposite side is equal or proportionate to the sine of any other angle over its opposite side. And of course, here in this chapter, we're dealing with non-right triangles. Number two, the law of cosines states that the side squared, so c squared, of a triangle is equal to the square of another side, a squared, plus b squared, the square of the third side, minus 2 times a times b times cosine of c. That's a bit more involved of a law. But notice if you do have a right triangle and the cosine of 90 is 0, then that term disappears and you have good old regular Pythagorean theorem, which of course is where the law is derived from. The third rule we'll be looking at is the area via trig of a triangle, which is 1/2 a times b times sine of c, c being the angle included, in other words, the angle formed by sides a and b. Okay, so let's say you get these three rules, right? Got them. But then you turn to question number 17 on page 363. And our job here is to, again, to find the area of a plot of land. I'm going to go ahead and read the question in its entirety first. And then we'll focus on drawing the picture, sketching the plot of land, and then we will apply these formulas to solving for the area. So, number 17, surveying. From the southeast corner of the cemetery on Burnham Road, proceed south 78 degrees west for 250 meters along the southern boundary of the cemetery until a granite post is reached. Then, essentially turn 15 degrees east of south and proceed for 180 meters to Allard Road. Then turn, essentially 78 degrees east of north along Allard Road until it intersects Burnham Road. And finally, go 30 degrees east of north along Burnham Road back to the starting point. Okay, seems simple enough. But let's take a closer look. So first we have to draw the figure. Let's arbitrarily start up in this corner here. So let's say this is our starting point. I'm going to use a slightly thinner pen for this because you'll see there's some really complicated parts here of this question. So let's start here. And when it says proceed 78 degrees west of south, well, essentially that means make a little north-south, and instead of going due south, go 78 degrees west of south, which essentially is going to look something like this. Close to the horizontal, we're gonna go out to here. All right, and it says do that for 250 meters, or is it miles? Meters. That would be an enormous cemetery. Okay, then we reach the granite post. Oh, there's our granite post, and here up here, of course, is our cemetery because we were at the southeast corner of the cemetery. And then it says we're going to go 15 degrees east of south. So again, you can kind of just sketch a little T and just kind of eyeball 15 degrees east is going to be like so. Oh, it's a little much. So let's try that again. We want to stay pretty close to that. Well, that'll have to do. So we're going to do that for 180 meters. All right. And that's until we hit Allard Road, at which point we're going to go 78 degrees east of north. So we'll sketch another little, and then 78 degrees east of north is like this. In fact, this line ends up being parallel. Well, let's not worry about that. We're 78 degrees east of north, which really means, okay, so just so we're clear what's going on here on these turns, this is 78 degrees right here. And we're going to take a much closer look at all of these corners in just a moment. And then 30 degrees east of north until we hit Burnham. Well, if you think about it, that's probably going to be more like over here. All right, so let's put our little guy here. And then we're going to go 30 degrees north, which is just about like so, until we get back to our starting point. So not bad. And again, this would be the 30 degrees here. All right, so now we have a parallelogram. Notice we have an angle here and a composite angle here made of those two. We have another larger angle here. And of course, we have one here in this corner. So what are those angles? In other words, what are the angles of our parallelogram? Well, I think in a lot of ways that's the hardest part of this question. So I'm going to kind of slow down and we're going to take a look at each corner. This corner looks pretty good. In this corner, we knew that this right here, from here to here, was 78 degrees because, well, we were told that that was 78 degrees. And then because we know that this here is 30, and when you have these two north, south, east, west sort of coordinates here and here, there's a parallelism involved there. And so you're going to get your other 30 degrees right in here. You see this one here? That in there is 30 degrees. And then because we headed out 78, well, this does make a right angle, so there was 12 left over right here. All right, so again, because I think this is in large part the hard part of the question, I'm just going to sort of blow that up so we can see real quick. We headed out 78 degrees, so there was 12 left here. And then we came in at an angle at the end of 30 degrees. All right. So the 78, essentially 78 minus the 30 is what gives us our angle measure in here, which is 48. All right, and that's a pretty tricky part of the problem. So in other words, in our parallelogram, in our quadrilateral, this angle up in the corner is 48 degrees, which we will need. Okay, let's head over here. This one's a little easier. I'm going to enlarge this corner here. So remember, we came in at an angle of 12 degrees because, well, we left over here at an angle of 78, right, from over here. So 12, and then we left, we cut down here at an angle of 15. Get out of there. That was the direction there. So this was 15. All right, leaving what here? Leaving 75, right? So 90 minus 15 is 75. So essentially, this angle in here ends up being that 75 degrees plus the 12. Perfect. So we've got this one solved. This one's 87. All of this work is a little tedious, but I assure you the key to this problem is solving this quadrilateral correctly. Okay, down here again, I'm going to enlarge the corner here. Right, we came in at that angle of 15. Yep, all right, so that's derived from the previous corner. And then we departed at that angle of 78. All right, so 78. This was the 78 here. And so this corner here is going to be 78 plus 15, which comes to 93. I'll write that here. Okay, and then over here, I'll enlarge this corner just so we are clear. We came in from below, and we were told to leave at 78, so that leaves a 12-degree angle here, right? Which, just so we're clear, that's equivalent to this 12-degree angle here. Does that make sense? The leftover of what we depart on in this corner is going to be sort of what we're coming in up here. This is the 12 right here, if you see it. And then we have a right angle, so that's 90 degrees, easy enough. And then we were instructed to depart at an angle of 30 degrees as we headed back towards our original corner. So we'll say that's the 30. And so the sum here is a 12 plus the right angle of 90 plus 30. All right? And that angle then in this corner of our quadrilateral comes to 132. All right, so in many ways, solving for the 48, the 87, the 93, and the 132, although tedious, is one of the hard parts of this question. All right, I feel good about this. Let's move on. I have redrawn the quadrilateral up here on the big board, just noting the main degrees here. So that's 48 degrees, and 87, 93, 132. Now, let's get to the trig. So, because we're given 250, and we were also given this as 180 meters, you might remember. The first step of this problem is pretty simple. We're going to draw a dotted line here, dividing the quadrilateral into two non-right triangles, right? So we have a triangle up here, and we'll call the area of this A1, and we'll call the area of this A2. Well, the area of A1, fortunately, is pretty straightforward. The area of A1 is equal to 1/2, well, I'll write the formula, 1/2 A times B times the sine of the included angle. So what does that mean here? That means, well, 1/2 is the constant times that 250 meters along the top times the 180, sort of on our left, times the sine of the included angle, in other words, the sine of the one formed by those two sides, which we discovered on the previous page was 87 degrees. So not bad, right? It seems like we're halfway done. We're almost there. So plug that into your calculator, and you'll get 22,469 meters squared. Okay, now we have a more interesting challenge, because we don't know the length of Allard Road that we travel, nor do we know the length of Burnham Road. Frankly, nor do we know the length of that dotted line through the middle of the quadrilateral. And besides the angle 132, we don't know how to break up those other two angles, 48 and 93. We don't know how to break those up so that we know the angles just of our triangle A2, the one marked with area 2. So here we have to use some nifty triangle geometry. So let's change colors, do a little green. And our step 2 is the law of cosines. So remember, the law of cosines says that c squared, and we're going to say c squared is this big long line here, all right, the dotted line. We're going to say that's c. And we can use our information on this triangle, in other words, the 180 and the 250 and the 87, to solve for c. The formula says c squared is 180 squared plus 250 squared minus 2 times, that's a parenthesis out of control there, times 180 times 250 times the cosine now of that 87 degrees. And of course, make sure you are in degrees for this question. And you can plug this into your calculator. C squared comes out to 90,190. But to save room, we're just going to say the square root of that 90,000 is 300. And I'm going to go ahead and put some decimals, and I'll explain why later. But it's basically 300 meters. So we've solved for C using the law of cosines. Not bad, right? I'm just going to write 300 here. That's our dotted line. Okay, so how much closer are we? Well, again, we still don't know these angles, right? I'm going to kind of notate them here in a different color. We'll go to orange for the angles. We don't know this or this, the breakdown. Nor do we know this part of this. So we can't really solve for the area of A2 until we figure that out. Okay, so let's do so. Let's use the law of sines. So we'll start with using, again, the triangle that we know more about. So we're using this 87. This 87 is going to get used for the third time. That was a big piece of our knowledge. So the sine of 87 degrees, right, over its opposite side, which you'll notice in the A1 triangle is 300, what we just solved for, is equal to the sine of, well, let's just call it x. We'll say the sine of x, and we'll call this angle up here x. Where is my cursor? We'll call this x right here. So I mean the portion of 48 that is in this top or left triangle. So that'll be over its opposite side, which is the given 180. So again, you cross multiply, and you get sine of x equals, well, about 0.599. You can just plug that in your calculator. And so angle x, when you do the inverse sine of both sides, is 36 points. And again, I'm going to write out a bunch of decimals here. But, you know, about 36.7 or 0.8 degrees. All right, so great. We're moving right along. We've got this one to be, I'm going to write 36.8. Okay? Now, it's easy enough to solve for this little guy. We'll call this one y. And, you know, that's just going to be 48, right? 48 minus the 36.8, which equals 11.2. Okay, so y right here is 11.2. Good? All right, now that we know that, of course, we can solve for this angle. Let's go ahead and solve for this side. You see, we know enough now. We can solve for the length of Allard Road, which let's go ahead and call A. In fact, let's use a different color here. We're going to be solving for length, so let's go back to our red. So Allard Road we'll call A, and Burnham Road we will call B. Makes sense, right? And we can continue to use the law of sines to do so. Not bad. So let's just do it right up here. We can set up a law of sines using this 132 that we saw from the previous page, right? So sine of 132 over that 300 that we found using the law of cosines is now going to be equivalent to the sine of that 11.2, or with all proper decimals, 11.23, over A, over the length we travel on Allard Road. Not bad, right? Cross multiply, and right away we get A equals 78.7288, and that's in meters. So there we go. We've solved for A. We travel along Allard Road for about, oh, let's say 78.7 meters. We are almost there. Stay with me. Keep in mind that you may own land one day, and of course you will pay taxes based on the size of the plot of land you own, and maybe you think that your surveyor is a little off, and you might want to go out there and do a little surveying yourself and see if you can't lower your tax bill. So of course, as always, math is applicable and relevant to real life. All right, lastly, let's go ahead and solve for B. That's another straightforward application of the law of sines. We're going to again use this sine of 132 over 300 ratio, which is now equal to, yes, how do we get this angle down here? Well, it's just a triangle, right? So I'm going to do my simple little math over here. 132 plus 11.2, well, that's 143.2, and then 180 minus that, right? I'll just kind of jot that here, 180 minus that, right? That gets us angle, I guess we'll go ahead and call it 36.8. All right, so that's the angle in this corner, which we now need here, sine 36.8 over B, Burnham Road, right? That's its opposite side in this other triangle. Go ahead and cross multiply, and voila, we've got the distance now that we travel along Burnham Road, which is about 241.9, or we'll go ahead and write 242. All right, we are only moments away. We're going to solve now for the area of triangle 2, which of course was our ultimate goal. That combined with the area of triangle 1 is the answer to the question. So again, 1/2. Now we have A was Allard Road, and the length we traveled there is 78.7. B was Burnham Road. I'm going to write it was about 242. And that area comes out to, don't forget, times the side of the included angle, which is the 132, which we've had for quite a while. Had that on the previous page. So that area comes out to 7,076. I'm going to give some decimals, 0.55. So, final answer. Area of the plot equals A1 plus A2, which we have used all of our knowledge of triangle trigonometry to discover. And the final answer, in my humble opinion, is 29,545.6 meters, and of course meters squared because it's an area. So, there you have it. Now, in the back of the book, in the back of old Richard G. Brown, the answer is 29,600 meters squared, which to me is a bit of a mystery how they rounded up. It seems like we were about 5 meters squared away from rounding up. So extra credit to any of my viewers, to any of my motivated viewers. Go ahead and do this problem again. Pay close attention to your decimals. Save your second answers when moving forward and solving the next part. And let me know how you get to 29,600. But in the meantime, hopefully this is a good review of how to put together everything you know about Chapter 9 and triangle trigonometry in order to solve a difficult question about surveying a plot of land. And hopefully, one day this knowledge will maybe help you save a little money on your taxes. As always, thanks for watching, and I'll see you in the future.